Okay, this is functions number 3, composition of functions. Since functions convert the value of an input variable into the value of an output variable, it stands to reason that this output could then be used as an input into a second function. This is known as composition of functions. In other words, combine the actions or rules of two functions. A circular garden with a radius of 15 feet is to be covered with a topsoil at a cost of $1.25 per square foot. Determine the area of this garden to the nearest square foot. First, to determine the area, we need to find out what shape it is. It is a circle. The area of a circle is pi r squared. The radius is 15, so we're going to plug in 15 for r. So the area is going to be, it's a very windy day out here, sorry for the noise. The area is going to be pi times 15 squared. Plug that into your calculators and you get 706.858. So the nearest square foot is 707 feet squared. We're going to use our answer from part A to calculate the cost of covering the garden with the topsoil. So we have 707 feet squared, and each feet squared costs $1.25. So we'll multiply on our calculator, and that gives us $883.75. So we saw that the output of the area function was used as the input to the cost function. Using the diagram below, we're going to generalize for generic functions how this is done. Our input's going to be x, and our output from function f becomes our input for function g, and then that final output is going to be our final y. There are two different notations that are used to indicate a composition of functions. We're going to introduce them in the next few exercises with both equations and graphs. Given f at x is equal to x squared minus 5 and g at x is equal to 2x plus 3, we're going to find each of the following values. For A, we want f of g of 1. So first we need to find what g of 1 is. So instead of 2x plus 3, it's 2 times 1 plus 3. You may also use store, and our answer is going to be 5. Now we do f of 5. So that'll be 5 squared minus 5. Again, you may store 5 for x and then put in x squared minus 5, and that is going to give us 20. Okay, g of f of 2. Do f of 2 first. So that'll be 2 squared minus 5. Again, let's store 2 for x, do it in our calculator, and we'll get a negative 1. We have g of negative 1, so that's 2 times negative 1 plus 3, and that is equal to 1. Okay, first we do g of 0. 2 times 0 plus 3. It's going to give us 3. And now we do g of 3. So it's 2 times 3 plus 3, and that is going to give us 9. The other type of notation that we use for composition is f, little circle symbol, g, and that is read f of g of negative 2. We're going to go from right to left. So first, we're going to do g of negative 2. It's 2 times negative 2 plus 3, and that gives us a negative 1. And now we do f of negative 1. Make sure you put the negative 1 in parentheses, or to avoid any mistakes, use store. Okay, f of 3. That'll be 4. And now we do g of 4. Okay, we're going to do f of negative 1. Again, it's crucial that you put that negative 1 in parentheses, or like I said before, to avoid any errors, you may use store. Show the substitution, but use your calculator using store. Okay, we're going to use the graphs below. This is my f at x function, the line, and on the right is my g of x function, my parabola. Okay, so we're going to find f of 2. So let's go to our function f and see when x is equal to 2, what does y equal? So here's the point I'm going to use. When my input is 2, my output is going to be 3. So f of 2 is equal to 3. Now we do g of 3. So let's go to my function g graph. And when x is equal to 3, 1, 2, 3, that's my point there. My output is also going to be 3. So g of 3 is equal to 3. Now we'll go to g at negative 1. So let's go to our graph. When x is equal to negative 1, on our graph of g, what is y going to equal? So that's the point I'm going to use. When x is equal to negative 1, y is equal to negative 5. So g of negative 1 is negative 5. Now we find f of negative 5. Let's go to my linear graph. When x is equal to negative 5, what is y equal to? So we'll go to negative 5. So it's about there. I would say that's about negative 1/2. Okay, g of 1, let's go to our graph. That's our point there, so g of 1 is equal to 3. Now we go to the same graph and look for g of 3. And that point's already been marked. That is going to be also 3. Okay, f of negative 2. Again, look at your graph. That's our point there. When x is equal to negative 2, y is equal to positive 1. So f of negative 2 is equal to positive 1. And now let's go to g of 1. We've already determined that to be equal to 3. Okay, let's go to g of 0. Remember, that would be our y-intercept. And g of 0 is equal to 0. So g of 0 is equal to 0. And f of 0, again, that is our y-intercept of the function f. Go to that point there. So when x is equal to 0, y is equal to 2. Okay, what is f of 0? Well, we just determined that. That was equal to 2. Now we want f of 2. And again, f of 2 we can see is equal to 3. On occasion, it is desirable to create a formula for the composition of two functions. In the next two exercises, we will illustrate this process by finding these equations with simple linear and quadratic functions. We're given the functions f at x is equal to 3x minus 2 and g at x is equal to 5x plus 4. Determine the formulas in simplest y is equal to ax plus b form. So we must simplify at the end. We want to find f of g of x. So that means into function f, we're going to plug in function g, which is 5x plus 4. So wherever there's an x in my function f, we're going to plug in 5x plus 4. So it's going to be 3 times 5x plus 4. We're going to distribute the 3 and then simplify. So it'll be 5 times x times 3 is 15x plus 12 minus 2 is 15x plus 10. Now we want to find g of f at x. So into function g, we're going to plug in f at x, which is 3x minus 2. So wherever there's an x in function g, we're going to plug in 3x minus 2. So it's going to be 5 times 3x minus 2 plus 4. So it's 15x minus 10 plus 4. And that simplifies to 15x minus 6. If f at x is equal to x squared and g at x is equal to x minus 5, then find f of g of x. So we want f of x minus 5. So instead of x squared, we're going to do x minus 5 squared. It would be x minus 5 times x minus 5. So it would be x squared minus 5x minus 5x plus 25. And that simplifies to x squared minus 10x plus 25. And that is choice 4. If g at x is equal to x plus 3 and f at x is equal to x squared minus 2, find the value of f of g of a. So first we'll do g of a. So where there's an x, we're going to plug in an a. So a plus 3. Now we want f of a plus 3. Instead of x squared, we're going to do a plus 3 squared minus 2. So that'll give us a squared plus 3a plus 3a plus 9, and let's not forget our minus 2. And that becomes a squared plus 6a. 9 minus 2 becomes positive 7. Okay, first we're going to find f of 3. And that is equal to 5. Now we find g of 5. And that is equal to 4. Okay, we're going to do f of 2. F of 2 is equal to 4. And now we want f of 4. And f of 4 is equal to 6. Okay, g of f at x is equal to 8. So this means that g of x is equal to 8. Sorry about that. So let's go to, okay, so when g of x is equal to 8, let's go to our table and find where g of x equals 8. So here's where g of x is equal to 8. X is equal to what number? 7. So x is equal to 7. So therefore, now we look where f at x is equal to 7. Okay. When f at x is equal to 7, x is equal to 5. And for D, which I apologize is not on here, but it is on your sheet of paper, what is f of f at x is equal to 6? Well, when f at x is equal to 6, x is equal to 4. And when f at x is equal to 4, x is equal to 2.